You will never fall into a black hole, almost certainly. But your atoms might, eventually. And what happens to them, what happens to you, is one of the strangest, most violent, most philosophically disturbing stories in all of physics. Let's walk through it, step by step. What a black hole actually is. First, forget everything you picture. Not a hole, not empty space, not some cosmic drain waiting to swallow the universe. A black hole is an almost unimaginable concentration of mass, crushed into a point so small, our mathematics refuses to describe it. A singularity. The gravity it produces is so extreme that beyond a certain distance, the event horizon, nothing escapes. Not matter, not light, not even information. And here is the part people get wrong. The event horizon is not a wall. It has no surface, no texture. You cannot see it. If you fell through it, you would not feel it. There is no membrane, no alarm, no dramatic flash of light. Just a point of no return, crossed without knowing. Let's say you are falling toward a stellar black hole, the kind born when a massive star collapses. Mass roughly 20 times our sun, compressed into a sphere about 120 kilometers across. From a distance, it looks like nothing, a dark circle, stars bending around its edges, their light curving like water around a drain. Visually, almost beautiful. But as you get closer, something subtle begins happening to time. Gravity warps space-time. The stronger the gravity, the slower time moves, relative to anyone watching from a safe distance. This is not a metaphor. This is not science fiction. This is measured, confirmed, everyday fact. GPS satellites have to correct for it constantly, or your maps would drift by kilometers within a single day. Near a black hole, this effect becomes extreme. From your perspective, falling inward, everything feels normal. Time ticks at its usual pace. You feel weightless, free, the same way astronauts feel weightless on the International Space Station. But from the perspective of someone watching you from a safe distance, you slow down. Your movements become sluggish. The light reaching them from your body shifts toward red as it struggles to climb out of the gravitational well. You appear to freeze, to redden, to fade. To them, you never quite cross the horizon. You just asymptotically approach it, dimming, slowing, disappearing into red silence over billions of years. To you, you cross it in moments, and nothing feels different. At first. Here, physics tries to kill you. This is the part that ends you. Black holes do not kill you with pressure. They kill you with the difference in gravity across your body. Here is how it works. Gravity follows an inverse square law. The closer you are to a massive object, the exponentially stronger the pull. So if you are falling feet first toward a black hole, the gravitational pull on your feet is significantly stronger than the pull on your head. Even across the length of your body, roughly 1.8 meters, the difference is enormous. Your feet accelerate faster than your head. Your body stretches vertically. The same force compresses you from the sides, squeezing inward while pulling you apart lengthwise. You become, quite literally, a strand of matter. Your cells tear apart, your molecules separate. Your atoms are drawn out into a long, thin stream, like toothpaste squeezed from a tube, spiraling toward the singularity. Physicists actually call this spaghettification. That is the real technical term, and it is as catastrophic as it sounds. For a stellar black hole, the smaller kind, spaghettification begins before you even cross the event horizon. The tidal forces are so extreme that you are already a ribbon of plasma long before you reach the point of no return. For a supermassive black hole, the kind sitting at the center of galaxies, millions or billions of times the mass of our sun, the event horizon is so large that tidal forces at its boundary are actually gentle. You would cross it intact. You would have hours, maybe days, of free fall inside before the spaghettification began in earnest. Hours inside a black hole, falling toward a singularity, no possibility of escape, no possibility of communication. The universe outside, unreachable. Time behaving in ways that make no intuitive sense. That is a specific kind of horror. Here, physics breaks. At the center, physics breaks. Not metaphorically, literal. The equations that describe gravity, general relativity, produce an infinity at the singularity, infinite density, infinite curvature of spacetime. And whenever a physical equation produces an infinity, it means one thing. The theory has reached the edge of its own validity. It is telling you it does not know what happens here. We do not know what a singularity actually is, whether it is a true geometric point, whether space and time cease to exist as meaningful concepts, whether something else, some deeper layer of physics we have not discovered yet, takes over. What we do know is this: your atoms, your molecules, your information, everything that was once you, reaches this point and encounters something our best science cannot describe. The information paradox. Here is where it gets philosophically brutal. In quantum mechanics, information cannot be destroyed. The state of every particle, its position, momentum, spin, encodes information about the universe's history. Even if matter is rearranged, burned, scattered, the information is preserved somewhere, in some form. This is a foundational principle. Black holes appear to violate it. When you fall in, your information falls with you. When the black hole eventually evaporates, and they do evaporate, slowly, over astronomical timescales, via a process called Hawking radiation, the radiation that escapes appears to be completely random, carrying no information about what fell in. Your information, the quantum description of every atom that made you, appears to simply vanish. Stephen Hawking spent decades arguing this was true, that black holes genuinely destroy information. Most physicists refused to accept it. It became one of the most heated debates in modern theoretical physics. The current leading idea is that information is somehow encoded in the Hawking radiation, subtly, invisibly, in correlations too complex to read, that nothing is truly lost, that you, in some incomprehensibly scrambled form, eventually leak back out into the universe over trillions of years as faint radiation. Not you, not anything recognizable, but the information that described you, preserved, transformed beyond recognition. Hawking radiation has never been directly observed. The debate is not fully resolved. We genuinely do not know what happens to you at the deepest level. The view on the way in. One last thing, because it is extraordinary. As you fall toward the event horizon, gravitational lensing compresses your entire view of the universe into a shrinking circle of light directly ahead of you. The rest of the sky darkens. Stars that were spread across 360 degrees compress into a single bright disk, blue-shifted, intensifying. You see the entire observable universe, billions of galaxies, billions of years of light, compressed into a shrinking window. Then the window closes, and you are inside, alone, in a place where the future points only one direction, toward the singularity, where escape is not physically possible in the same way that moving backward in time is not physically possible for us. You are not trapped. In the geometry of space-time inside a black hole, falling toward the singularity is simply what moving forward in time means. There is nowhere else to go. Black holes are not monsters lurking in the dark, waiting to devour the universe. They are places where the universe reveals its own limits, where our best understanding of reality quietly admits it does not have all the answers, where the rules we built everything on stop working, and we have no idea what is on the other side.